9,000 terawatt hours demand per year. So imagine that today, PLN or Indonesian electricity demand is about 3,000, no, 300 terawatt hour, I mean. So it will be 30-fold from current demand. So assuming that capacity factor of solar PV in Indonesia, 15%, this 9,000 terawatt hours is must be generated from 6.7 terawatt of solar PV. Each terawatt PV will produce 1,400 terawatt hour per year. So as I said previously, the task or what the problem addressed in this paper is where to put 6.7 terawatt hour solar PV panels. So does Indonesia has space for that? So that's what we seek in this paper. So I would like to share about this, why Indonesia need to think about use its solar energy potential, because last year or 2020, we can see in the left chart here, this is the solar PV, wind and other renewables. If it's compared to fossil fuel and nuclear power plant additional capacity, more than half it's already renewables. If we combine solar PV, wind and other renewables, it's become around 75%. So more and more countries globally use renewable, especially solar PV and wind, because the cost is dramatically fall. So if we look at details about what per person of renewables over the world, Netherlands will be the highest. So it's around 300 watts per person per year. And Australia here, it's about 260. If we look more details, solar PV is the biggest portion of it. Like here in Netherlands, or let's say Australia here, it's around 170 watt per person per year. So where is Indonesia? If we look at this, where is Indonesia? Indonesia is quite, or we can say it's nearly zero because it's so small. It's only 160 megawatts roughly. So if it's divided by the number of Indonesian population, so it will be very, very slow, very, very low. We can't even see the chart here. So this is if we compare about the other country and Indonesia. So as I explained in the previous slides, what we want to address is if we want to use or we can move to solar energy, where to put the panels. So Indonesia, you can see in this map, Indonesia consists of 17,000 islands. The land area is about 1.9 million kilometers square, and the ocean or the maritime area is 6.4 million square kilometers. So actually we have a big land area or a big sea area. So is that true that we don't have land to put our panels? So let's see in the next slide. Yeah. Before we go to the where we put the panels, I will show you about what we already found about the previous studies. So here you can see that many studies, like studied or not studied document, a government document, RUEN, National General Energy Plan, it says that solar PV potential is 200 gigawatt, or here a study by Veldis and Reinders, it says 1,000 gigawatt. A study by Irena says about 500 gigawatt, and also from the World Bank is nearly the same, 500 gigawatt. IESR recently published a paper that only for residential rooftop solar, it's in the range of 200 gigawatt up to 650 gigawatt. Actually, there's a study that's saying it's much bigger than the previous. It's studied by Fidinopoulos et al. It says that Indonesia has a 19 terawatt solar PV potential. So it's equal to 26,000 terawatt hour per year. But what I could conclude from what the studies present is that they apply strong and unnecessary constraint on siting of solar panel. That's why the solar power potential is much smaller than estimated in this paper. So we can see that in the summary later. Yeah, so to address the question where to put the panels, so at first we look at the mine regions. Do we have a significant area there? So we use a global data set of mining from Moss et al. It's a study from 2 years ago. It's about how to make a delineation or like here in the red line for all the mining area all over the world. So in Indonesia, Moss et al. Said that Indonesia has about 3,600 square kilometers mining area. And then we also look at the OpenStreetMap. It says that Indonesia has a quarry area of about 730 square kilometers. By combining both of this data from Moss and from OpenStreetMap, we eliminate the overlaps. So we found about 3,900 square kilometers. So this is the area that's active mining area. So we use also a Landsat 8 image from USGS, from US websites. It's geological, I think. It's from 3 years, 2018 up to 2020. We look at all the mining area in Indonesia. We choose the clear image without cloud covering. So we try to extract or to classify all the mining areas within this red line, which is disturbed land or the water area. So like the picture here, the image here, the left side is an image from Landsat 8, and then we use a GIS, a quantum GIS, a free software, and we classified this area to find out how big the vegetation area. It's represented by green color, and also, you know, sometimes in the former mining area we can find a small lakes or small reservoir. So it's represented by blue color here, and the land area is the brown color. So we look for from 3,900 square kilometers, how big the water area and the disturbed land that we propose to host the solar panels. So we found about 2,300 square kilometers there. The other potential is the location that we can use is how to install the PV panels using the same area with the crops, the agriculture area. So agro-photovoltaic or APV, it's a combination of solar panels and also crops in one area, let's say like here. It is a study by Sekiyama, it says that there are 3 options if we want to install PV panels collocation with agriculture. So it is in between of the crops, or we use like greenhouse, we put the solar panels on top of the crops. And also the last one is using like a steel mounted, it's using a structure like here. So we can place the panels on top of the crops. So maybe it's the purpose is how to the machine or the tractors, like whatever the tools that the farmer use, it can be moved around here or above here, not disturb the crops. So using data from Indonesia statistics or BPS, we find that 210,000 square kilometers, Indonesia had a low growing crops. What's the low growing crops here? It's a maximum height of 5 meters or less. So it's like a rice, coffee, corn, or others, yeah, like tea or potatoes and other kind of crops in Indonesia. So if we apply like 10% or 30% to cover these crops, above the crop we install solar PV, but we don't include rice here because we think that rice is a main food in Indonesia, so we don't want to reduce the production, because according to the studies, it says that if we put something above the crops or we cover it, it will be a shadow effect. It can reduce the production of the crop. So with this assumption, a panel area of 11 up to 31,000 square kilometers will become available. This is equal to 30 up to 90% of the required land of 35,000 kilometers square. The other potential location is floating solar. So where to put the panel? So imagine that Indonesia has a lot of lakes like Toba Lake or Sentani Lake in Papua, or maybe in Sulawesi, we know Lake Poso or the other lakes. And also we have a lot of reservoirs like Cirata reservoirs in West Java or in the other places. So using a GIS survey, a combined area of lakes and reservoir is about 5,000 square kilometers. This is excluding the protected areas. So you know that some part of the lakes is not all, but sometimes it's 20% or 30% of the lakes is part of a protected area. So we exclude that from our calculation. So using under current regulation that only 5% a maximum area can be used for solar PV, it's still, we have around 250 kilometers square for solar PV. It's equal to 50 gigawatt. So you know that installed capacity today in Indonesia is around 70 gigawatts. So imagine that only using this fresh water, we can have a little bit less, yeah. So 50 gigawatt. So it's little from the future requirement. It's 0.7, but it's still a big number. And then we also look at the maritime area. So we look at the sea, but the problem is if we install PV panels floating on the ocean, we have to be aware that's how the safety of the installation. So we have to look at the maximum wave height there. So we use 40 years data from European agency. It's ECMWF, it's ERA 5 data. So a total of all the area of inland sea in Indonesia, we divided it into 2,400 pixels. We analyzed that, and we found that most of the area of Indonesia is let's say it's the maximum wind speed is only around 20 meters per second, like we can see in this table. So if we move from 10 meters per second, the area is about 40,000 kilometers square. And if we look at which area is the maximum wind speed, sorry, it's yeah, so I think it's the previous, no, not the previous. Yeah, sorry, it should be this table. So I will explain this. If we look at the 2 meter wave height, we have around 180,000 square kilometers. And then if we look at the area, how big the area that Indonesia has for 4 meter wave height here, it's become around 6 times. So it's 847,000 square kilometers. So the point is that Indonesia, if you want to install the solar PV on the ocean, we should be careful about the wind speed and also the wave height. So if we combine the maximum wave height and also the maximum wind speed in Indonesia using the data from the European agency, so we can see that this is the area that we can say which area is the most safe for Indonesia. Let's say if we only use 2 meters wave height and wind speed 10 meters per second, we have 23,000 kilometers square. And if we look at 4 meter wave height, 10 meters per second wind speed, it's become 38,000 kilometers square. So in this study, we assume that the most safe place for Indonesia is 4 meter wave height and 15 meters per second wind speed. So this will be around 700,000 kilometers square. And as the assumption in the previous slide that we only need 35,000 kilometers square. So we have around 20-fold of that we need to have a fully renewable energy supply for Indonesia. Let me continue. Yeah. The last one is that Indonesia also has the potential of urban PV, or we frequently say it rooftop PV. So if in this study, we adopt a range of 1,500 up to nearly 4,000 watts per person. It's with assumption that in the future, Indonesia will be prosperous. So we have a high income and all the people will use rooftop solar. So it's equal to the range of 2 up to 5 megawatt hour per person per year. We assume the capacity factor of solar PV 15%. So this amount is equal to 7 up to 19% of the upper bound of energy requirement in 3 decades from now. Yeah, so in this study, as I mentioned, the novelty is also about the pumped hydro energy storage. So in your screen, you can see that Indonesia, this is the map of Indonesia. So this red circle and also yellow or orange circle is representing the sites that potential for off-river pump hydro storage. So in our study, there are 26,000 sites we identified that the most suitable for pump hydro storage. So this is like finding a upper reservoir and lower reservoir, but it's not as part of the river. So it's not like if you ever heard about upper Cisokan, it's in the body of the river. So it's not like that. So this is like if we have topographical area, we have a hilly area and also a valley. So we combine that and then we can build a reservoir on top of the hill and also in the valley. So we connect that with a tunnel, so we can use that as a closed loop system for pump hydro storage. So the number is about 8,000 terawatt hour. So this is in our analysis is about 30 times more than enough to back up or to balance the 100% renewable energy system in Indonesia with high penetration of solar. So this is will answer the question, or maybe people asking about how about the intermittency. So the answer is using battery, and the battery here is pump hydro energy storage. So as a conclusion, I will give the summary of the potential area for siting the solar panel in Indonesia. So you can see in this table. So the biggest area is what I want to highlight is on the ocean. So if Indonesia use its ocean as inland sea, it's relatively safe. It's only maximum 4-meter waves in 40 years period, and also 15 meter per second wind in 40 years period as well. We can have 700,000 square kilometers. So this is about 20 times that what we need. We need only 35,000 square kilometers, but we have 20 times of it. So if we can see also for the freshwater lakes and reservoir, assuming 5% coverage, it will be around, let's say, 1% of the future demand, the optimistic predicted demand in 2050. We still have about 50 gigawatt, as I mentioned before. And also for the mining area, the former mine area, it's 7% of the future needs. For agricultural photovoltaics co-location with crops, it will be around 30 up to 90% of the future needs. And future urban solar PV rooftop, if we assume that all people install solar PV, it will be 7 up to 20% of the future energy demand. So this study simply said that Indonesia has a huge potential of solar PV, and the upper bound of the needs, the energy, for example, here we assume 9 megawatt hour per capita. Current demand is 1 megawatt hour per capita. Even if we achieve the 9 megawatt hour per capita, the potential is more than enough. So actually no worries about the future if we want to, let's say, to achieve the net zero emission. So this paper says that also Indonesia has the battery storage, the pump hydro storage as the backup, or how to balance to answer the doubt for the intermittency for solar PV. Yeah. So these slides conclude my presentation. So I would be happy if you have questions. So I will give it back to Ibu Monica to lead this discussion. Thank you.
Thank you very much, Pak David, for the comprehensive presentation. Now, because I don't see any question from the participants here, allow me to invite our first expert here, Mas Antonius Yongki. He will share his view, feedback to the study. A brief introduction about Mas Yongki. He is specializing in performing wind and solar measurement and resource assessment, ensuring quality and integrity of wind and solar data collection, also analyzing the option and configuration of wind turbines and solar PVs to obtain the layout optimization and also the annual energy yield. He obtained his master's degree in renewable energy from École Polytechnique in Paris, France, and KTH Royal Institute of Technology in Stockholm, Sweden. He obtained his bachelor degree in mechanical engineering from the Bandung Institute of Technology, or ITB. Okay, so without further ado, hello, Mas Yongki.
Yeah, hello, Mbak
Hello.
Monica.
Yes, yeah, over to you.
Yeah, thank you for the time. And just want to confirm if you hear the voice clearly.
Yeah, I can hear
Yeah.
you.
Okay, and first of all, I would also like to thank Pak David for the presentation to explain in more details the potential of the resources of solar irradiance and land in Indonesia, which can help us to accelerate the development of solar projects. So please allow me, Pak David, to provide with some comments, which I mostly divided into two categories, technical and economic perspective. So the paper states that Indonesia annual electricity demand in 2050 is assumed to be 9,000 terawatt-hour per year, or 30 times higher than the current electricity demand. And to satisfy the demand, solar PV capacity of 6.7 terawatt and land or space of 35,000 kilometers square are required. So from the technical point of view, although the estimated required space is only 0.1% of the land area of Indonesia, we are interested to know more if the estimated area also considers the space for the battery storage system. We realized that the paper also uses pumped hydro as the energy storage. However, yeah, based on our study, there is also plan from PLN to study another type of storage, such as vanadium redox flow batteries, or RFB. And it's also interested to know how much the ratio of the land area for the solar PV versus battery storage system. As we know in our case, in our best practice, for 1 megawatt capacity, it requires 1.2 hectares of space. But because of the land title issues, the requirement of the land could be doubled. Also, out of the estimated 6.7 terawatt power generation, we realized that it's already 4 times higher than PLN estimation in 2050. And we also interested to know if there are any percentages of energy generations based on solar projects types, which are rooftop, ground-based, and also floating solar. To continue, also based on our best practice, when we make up the model in PVCs using irradiance from solar GIS, the soiling losses in the mining area or floating solar project could be higher due to more dust and also bird droppings, and also difficult to cleaning the surface respectively. And yeah, which also affect the power output, although we use the same irradiance as the inputs. So we are wondering if there are any differences on setting up the losses are considered in the modeling or simulation. And from the economic point of view, the study assumes that in 2050, coal, oil, and gas are entirely removed from economy. And we are also interested to know the consideration to make it faster than the plan from PLN, which is targeting to be carbon neutral in 2060. Also, as the paper includes the technical review on solar PV land requirement, consisting mine area, agricultural PV, marine area, or large water bodies. We think that it's also interesting to have study on the socio-economic perspective, as the land in Indonesia is complex, although it has a vast potential. It's really complex in terms of unbankable land tenure or ownership. So it's good if we have an estimation on the solar PV levelized cost of electricity, or LCOE, which consider also the land category itself. So in the end, we are going to have a priority or roadmap to develop the solar projects. I think, yeah, that's all what I currently have, David. And yeah, and thank you again for the opportunity to provide the feedback on this paper. And hopefully it helps.
Thank you, Mas Yongki. So before proceeding to the second expert here, may I ask Pak David if you have, do you want to share your feedback on what Mas Yongki has shared?
Thank you, Pak Yongki. That's really a tough question. First of all, I want to say that yes, the assumption in this study is the upper bound. So we imagine that Indonesia will be like Singapore 3 decades from now. So that is possible. So as you said, we remove all entire the fossil fuel from the economy, land transportation, heating, cooling, like industries for iron and steel making, and all the things. We assume the net zero emission for the economy. So that's really high compared to current electricity demand. Currently, we have 300 terawatt hour. In this study, we assume 9,000. So it's 30-fold. So it's really high. Yes, you're right. So, but this study purpose is, again, is to find, do we have enough space if we imagine that in the future Indonesia is electrified using solar PV. So even if we have 1 megawatt hour per capita, 3 megawatt hour per capita, 6 or 9, we can do that. So we can use the solar potential that we have. So back to your question, how about the pump hydro storage? How much the land occupied by that? So in this study, we assume, or based on study in Australia, that the needed storage is only 1 day or 24 hours, because Indonesia has no seasonal, like compared to, like, let's say Australia, we have winter season here, or like in Europe or in North America. So it will be easier for Indonesia because the variability is not big. So it's, we can say it's consistent from every province in Indonesia. We don't even need to interconnect all the regions. We can use it a single region. not really need Indonesian super grid, if you can say. So Indonesia will need about 25 terawatt hour. This is equal to about 2,000 square kilometers. So this is about 0.1% of our land. So it's really, really small. And you know that we can choose, let's say, from 26,000 sites, potential sites, we can choose the best one. We can choose it's not near the volcano, or it's far away from protected area, or we can choose maybe 1% of it. That's enough. So what I want to conclude to say is we have the potential for off-river pump hydro storage. And as I mentioned before, this is a low social impact. Imagine that if we use a conventional pump hydro like Upper Cisokan, how it's just like the normal hydro power plant. We need to flood, let's say, maybe 100 villages. And, you know, if we put something in the middle of the river, it will change the biodiversity there. The fish from the upper cannot go to the upstream, and you know, so many aspects there. So like environmental impact and social impact, using this off-river pump hydro, it will be minimized. I cannot say it's no risk, but I will say that it's very low compared to the conventional pump hydro storage. So this is the benefit if we use this scheme to build the storage to balance the variability of renewable energy in Indonesia. And about the loss of the solar panel, it's not part of this study, but we assume a 15% in our calculation is already include the loss, because as you said, bird drops and also from dust or for whatever, it's really impact the performance ratio. So we already calculated them in our assumption. So it will be in the future, because also we know that efficiency will become better and better. It will be around 200 watts per square meter. This is the moderate assumption. So we say that will be no problem. Yeah. So did I address all your question, or maybe I missed?
Yeah, maybe another last question, Pak, related to the extension of research related to socioeconomic or more depth analysis in the
yes,
in the economics.
All right. Yes. Actually, we plan to have another study for this. So at first, we did for the resource to answer, or to just, if we somebody or anyone that do you have the resource? So yes, we have. So the next step will we will come with an hourly analysis, the balancing the energy needs. So we will calculate the LCOE, and also we will try to minimize the social impact. Let's say if we have like a calm sea, why don't we use let's say HPDC transmission using undersea cable? So it's really different. It's compared to Philippines or for Japan. They suffer from typhoon frequently in a year. So we don't have it in Indonesia. So we have a big opportunity to, let's say if we build the conventional transmission, AC transmission, we need to procure the land, or, it's really a problem, for example, in Java with a dense population. So if we try to build that transmission just along the north of Java Sea, so it will be one opportunity as well. So in this study, we will address that. So I hope we can discuss that later on.
Yeah, sure, but yeah, that's also one of our interests to have your review on the economy of the solar projects based on the land category. So we really hope that it's going to publish soon, but so yeah, we can also use it as a roadmap or as a priority to choose which one the land that we need to prioritize in the development of the solar PV in Indonesia.
Oh, that's nice. So maybe we can have a separate discussion for that.
Yeah, sure.
So thank you. I'm sorry, I have to cut you here because we have another expert waiting. So without further ado, I would like to briefly introduce our second expert here, Mbak Prima Mangesti. She has more than 5 years experience in renewable energy development for both wind and solar projects together with Pace Energy, the subsidiary of Total Iron, involving in more than 3 gigawatt projects capacity development across Asia Pacific region. She performs in-house feasibility studies from site selection, resource assessment, yield analysis, and various technical study engagements. She is responsible to deliver on optimal and cost-effective site configuration. She obtained her degrees from Bandung Institute of Technology and University of Birmingham. Hello, Mbak Prima. Sorry, we have to make you wait for so long. So, yeah, hello, Mbak Prima. Yeah, over to you if you want to, if you have feedback to share with us.
Okay, first of all, hello everyone. Thank you for Energy for having me today. And first of all, I would like to greet David and Yongki as the speaker of this Paper Talk. Congratulations first for your published paper. I'm so honored that I can be one of the commentators, even though I'm very junior compared to you. So without long introduction, I would like to present some of the feedback for the paper.
Ibu Prima, I can't hear your voice clearly. I don't know if Ibu Monica can hear you.
Yeah, it's a bit broken.
Yeah, we can hear. It's like yeah.
Okay. Can you hear more clearly?
No, not yet.
Yeah, still broken. Maybe it's
no.
Yeah, maybe better to turn off for a while the webcam. Yes.
Okay.
Yes.
Okay.
Clear.
How about now?
Yeah. It's
okay.
Clear now.
Okay then. Okay. I will speak directly. Okay. Okay. So now I would like to present some of the feedback to the paper. Most of them will be maybe sharing of my experience, but please correct me if I'm wrong, but enlighten me if you have another view of it. Okay, so I think actually Pak Yongki has covered all of my question already actually, but I have some other interest in the paper. The first one is in the resource part of the paper, in the solar resource part. I read that you compare the PV potential across 34 cities. And I would like to know further, how do you choose the representative point of the GHI point or the resource point from the solar GIS or solar CAS for the sampling? Do you take the average value or maybe the higher one or something like that? And the second one, on the maritime floating solar part, because I come from meteorological background, so my background is mostly atmospheric science. So my view is true that typhoon or hurricane maybe will be a major issue in the solar floating deployment. But I think maybe for further research, you can add something like interannual or intraannual variability, because in Indonesia, especially in the inner sea, the impact of the interannual and intraannual climatological event like ENSO like dipole mode or something like that, will affect the wind speed and the wave height higher than the typhoon outside the inner sea, something like that. So maybe it's more like a suggestion. Then the third one, in your paper, you mentioned about the benefit of the agricultural solar benefit. It will be reduce the cost of the land. So please, can you elaborate more on that? And I want to share my view on that, because from our side of developer, we will see the agricultural solar will be more to like a CSR part of our project rather than an investment to reduce our cost of land. We all know that the cost of land in Indonesia is very high, and also it is like a social issue in every project of our plan in Indonesia. And especially in solar and wind, we will have like that kind of scheme that the unused land of our power plant will be handling by the community, and then they will they can use it for agricultural, something like that, which mean align with the agricultural PV concept. But it is more to CSR rather than investment for our project, something like that. And then the last one, I read in the paper about the mine region PV. Yeah, I have experience in the assessing PV or solar farm concept in the open quarry mine. So it was an unused mine, and then they offer us to build a solar farm there. But apart from everything, the main problem will be the slope at that moment. So how do you consider the slope or the topography of the quarry or the mines in the research for the mine region? So I think that's all from me. We'll be glad to hear your feedback. Thank you.
All right. Thank you, Bu Prima, for the question and also inputs for the feedback. So about the interannual variability, yeah, this is not considered in our paper. So it will be great if I can discuss this with expert like you. So actually, I invite some colleagues with a background of oceanography. So I asked what to consider if I want to install the solar PV on the ocean. So he said that at least you consider two things. Look at the wind speed and look at the maximum wave height. So because you cannot use the average wave height. So sometimes it has the highest value. So you must aware of that. And then that's what we did in our paper. So we look at the data for the European agency, although it's not data from the site, measured from the site, but it's kind of reanalysis. But the data agency said that it's quite good, so it's already validated with the actual measurement. So we assume that Indonesia have a calm sea, most of the Indonesian sea. So it's also confirmed if we look at the 50 years tropical storm in Asia Pacific. Indonesia has no, like, it's only in the northern part of Australia, or it's in the southern part of China, in Japan and Philippines. So it's not in Indonesia. And also the another thing that confirmed that Indonesia has a calm sea, that we must admit that we has a very low wind resource. So this is what not like disadvantage. Yes, there's disadvantage for wind power, but for solar power it's advantage. So that's what good about Indonesian Sea. So maybe we can discuss about that later. Of if I can find any studies about the interannual variability, I will consider that to reassess the potential that we found. So about the solar data, we get it from Solcast. So actually, I have the 34 cities for each province. Let's say for Aceh, I will use Banda Aceh to represent the province. For North Sumatra, I use Medan. For like South Sulawesi, I use Makassar, and all the capital of the province we use to represent. So because we see that from the solar GIS map, it's really not, the color is like average, not really different. So that's why we say that the solar resources is not the high quality, but we can say a good one. And the other thing is good and consistent. Let's say if Australia have a high quality, but they have winter season, they have problem with their seasonality. But Indonesia, in 1 year, every day is most of the average just the same. What this means? This means that we don't need a high backup or a high storage to cover the difference between winter and summer for Europe or Australia. So that will be our advantage as well. And about the agri-photovoltaics, yes, I agree with you that today, most of the project will be only a pilot or let's say the GSR. But let's think about how if we want to encourage a farmer to get more income. Maybe in West Java, like Karawang, we can find like a big area of rice field. So if they want to install on top of the rice, they get income from the rice itself, and also every day they can produce electricity. That means they get another income. So this is maybe not really technical, but it's more socio, yeah. You know that. About the mine area, how about the slope? Yes, that's the big challenge. So in this study, we are not looking at that because it's more will be like a feasibility studies, but we are thinking about to do that, to look at the most suitable area. But for this study, what we find is just like the open space without vegetation, because we don't want to disturb the environmental. So let's say if it's already covered by vegetation, just leave it. But if it's a barren area or nothing can live there, so we use that. And also another thing is, you know, that currently we have a regulation that we oblige that the developer of the mining or the owner need to reclaim. So if we propose, don't reclaim that, just put solar PV on top of the defunct area. This will be maybe one incentive, but maybe the problem now is, let's say most of the mining area will be in a south part of Sumatra or in Kalimantan. There's a low demand there, but maybe in the future we still can use that. Maybe at first we can use like fresh water, and then if we know that will be the ocean will be the next step, and also the rooftop and the mine area. Let's say if Indonesian capital is moved to Kalimantan, then it will need more energy. So why don't we use the former mining area? So yes, like this study is offer many options. So if you want to choose to install on top of agricultural land, you can do that. You want to put on your rooftop, that's okay. And also use mining area, that's even okay. Maybe you want to go to the ocean or to maritime area or freshwater like lakes and reservoir, that's also good for Indonesia. So basically we said we have all the resource, then start use it. This is what we want to ignite from this paper. Yeah, maybe that's my response for your feedback. Thank you, Ibu Prima.
Thank you, Pak, for the feedback also. Yeah, looking forward for your next paper.
Thank you.
Thank you, Mbak Prima and Pak David. So if I have to conclude, what is interesting here from the discussion is Pak David, through his study, would like to show the crazy idea, I would say, like if Indonesia have 100% renewable energy, it's possible. But it is also interesting to note that from Mbak Prima and also Mas Yongki that this is the reality from the field. Like we are faced with the reality of the land acquisition and also other social economic factor. So yeah, it's interesting to note that we have this in-depth discussion towards that. So I think it's already beyond beyond the time. So it's like 7 minutes beyond. So before continuing, may I ask if it's okay for our speaker here to stay for another 10 minutes, just to check if.
That's okay for me.
Yeah, sure.
Yeah.
Yeah, sure.
Yeah, thank you. So we have received like 4 questions from the audience, but I understand that the questions is I think already answered by Pak David, that this is beyond the scope of your study. So let me summarize and take it as like the suggestion or for your consideration for the next study. First is the environmental consideration. If we have the solar PV on the floating, if we have floating PV or wind, the environmental consideration, like what is the impact to the aquatic ecosystem, and also similarly has been raised by one participant here, that what is the impact to the marine ecosystem if we are having the floating system. Another thing is like you mentioned in your next study, you will also include the technical variability from the grid. There is one question that asking if the study consider like the load and transmission and substation. And also another question is to see how soon it is if we happen to install the solar panel in Java grid, because Java grid is like have the oversupply issues and also grid issues. So I noted that many things can be explored actually from the study, and we'll look forward to it, Pak. So before continuing, may I ask if there is anyone from the participant that would like to share feedback verbally? If none, I think I'm sorry, I have to conclude, because if we still continuing, I mean opening the floor for more questions, it will take maybe another 2 hours. So I believe you are also busy. So again, I would like to say thank you to our speakers here, Pak David, Mbak Prima, and Mas Yongki. And allow me for another 5 minutes to share the updates for the next ARNECC Paper Talks. Let me share my screen. Okay. Okay. So first, what I would like to highlight is, as usual, we have the ARNECC itself. ARNECC is a platform for scholars, analysts, researchers, students, and other stakeholders to share the related studies on energy and climate issues in Southeast Asia. The main objective is to facilitate interdisciplinary discussion like this of social, economic, governance, and technical issues. It is open to all researchers from any discipline or level of experience and not limited to any particular technology or sector or topic, but the boundary is Southeast Asia. So to register, please check the ARNECC webpage through the link provided here. And if you have further questions, please let us know by emailing to bennysuryadi@aseanenergy.org. Yeah. So next is 2 months ago, we launched the ARNECC Research Database, which aim to be a platform for the ARNECC member or any researchers that want their publication to be disseminated more effectively to the Southeast Asian readers. Please note that this database under the copyright term, so we are not like having the copy of your paper and publish it here. We just only link the DOI into our the DOI link to our database. Since the launch, we have received positive feedbacks, and now we have updated the database, reaching 150 more curated papers, and the numbers keeps growing. So we are inviting the researchers who wants to showcase their paper to simply submit details of your publication at the link provided here. Next is the ARNECC Paper Talks. So we have reached the 7th episode today. Next month we will have the 8th ARNECC Paper Talk, which is scheduled to be in the last week of October. Here we are also encouraging all the researchers who want their paper to be showcased to please send detail of your paper, short bio and photo to the accept.com.aseanenergy.org. Next, last but not least, I'm also inviting you and also you, the participants, and also the speakers here to please join in to ACE Think Tank Roundtable at Singapore International Energy Week, or SIU 2021, that will be held at Thursday, 28th October next month. SIU itself is a hybrid event available on-site and also online. For streaming, it is an annual platform for the professionals, policymakers, to share the best practices and solutions within the global energy problems. In this roundtable, we will bring experts from the private sector, academia, and government to discuss the needed actions and strategies to foster innovation in accelerating ASEAN's energy transition. We are pleased to share that we have the confirmation of the well-known speakers here. First is Eddie Tan, the VP of Semcorp, and also the second is Jennifer Kay, the partner of PwC, and also Dr. Retno Gumilang, the head of Research Center on Energy Policy of IPB. For more information, please check the link provided here. Okay, yeah. Now we have reached the end of our talk here. Again, I would like to appreciate our 3 distinguished experts here, Pak David, Mas Yongki, and Mbak Prima. Thank you for the insights. Thank you for the lively discussion, as well as sharing your valuable time and efforts for this event. Thank you for the active participation from the audience too. And I wish you to please stay safe and healthy, and see you again in the next month ARNECC Paper Talks. Thank you.
Thank you, Ibu Monica. Thank you.
Yeah,
Ibu
thank
Prima.
you.
Thank you.
Thank you, Pak
Thank you,
David.
David, Mbak Monik, Mas Yongki.
Yeah, thank you,
Mbak Prima, and
Mbak Monica, Pak David, Bu Prima.
yeah, see you again.
Yeah.
Pak Yongki, I'm happy if you want to discuss. Maybe we can set Zoom to discuss.
Yeah,
Yeah,
what
sure,
you
Pak.
mentioned.